So in this problem we have current in the infinitely long straight circuit, which is called C prime, and the current is given by some current amplitude and some time varying function. So this is the current in our source, marked with prime, and we need to find the induced EMF electromotive force that would be produced in a rectangular circuit, this one, of the same figure. And then what's the direction? What would be the direction of the induced current? EMF and the direction of the current. So electromotive force is a voltage. So we need to find the voltage induced in this rectangular circuit. So to do it, we can use the Faraday induction law. It's page 6. No, sorry, not page 6. Faraday induction found page 11. So EMF is in some sources is written as epsilon, or in some sources is written as V corresponding to voltage. So I think pages it's V induced. Let's write it like that. So V induced. Let's write this Faraday induction law. V induced is minus F. So this F is, it's not electric potential, it's a different F, maybe more like capital. And it refers to the flux, magnetic flux over the changing over time. Since we have a changing current, in time we will have also changing magnetic field and changing in time magnetic flux. So equation for the flux is also given there. Flux is directly related to magnetic field. Going through perpendicular to the surface. And here this surface, so in this case, either magnetic field can be time varying, or the frame, the circuit can be moving in time and then have time varying location, so to say. So we have the voltage we need to find. We have magnetic flux, so we need to find the B. And B, since we have a current, we can find using Ampere's law. This was page 5. B is page 5. enclosed current. So let's think about the magnetic field, how it will look. For the given current, so magnetic field, let's draw it. Will circulate around the conductor. So using the right-hand rule, direction of the current with the thumb, and then this is the direction of the field. And then we see that it's going perpendicular, this inside the board, perpendicular the circuit is this dimensions. So for this equation, then we can write that what is the B the loop and the closed loop over which we can integrate B is 2 pi r, the circle. Need to figure out the direction. Direction would be phi direction, right? So it will be B phi. In cylindrical system of coordinates. So we found the B. What about the enclosed current? We actually have a special value given for it. The enclosed in this loop, closed loop current is this time varying current. Okay, then we have this relation for the magnetic field, and now from this relation we can come to the flux. Flux must be perpendicular to be able to induce EMF in the circuit. So let's write that our B F direction of the B is phi. So also the normal to the circuit will be also phi. And then the integration will be along dr and dz. And then it would be equal to, let's take the constants out. So this is 1. So dr is what is that? We have the length b. Let's say from 0 to b. And would be easier. And for dr is from a plus d till d. from this point to this point. And then we will have here will be Z, then it will be B, and here we will have natural logarithm of R, so it will be natural logarithm of A plus D divided by D. That's a flux. The magnitude of the flux, magnetic flux through the circuit. And now the final, the EMF, electromagnetic force, negative sign. And then this is our flux. So oops. How do I have it there? This is a first mistake, horrible mistake. Because this is the value of the magnetic field. Have it somewhere? Yes. This was the value of magnetic field, which I substituted. Blue is gone. Okay. No, no, right. 2 pi r. Yep, the rest seems to be fine. Yes. Okay. So back to the corrected flux. So it should be time derivative of the flux. So what is time changing? Everything is constant besides this exponential. So let's write the constants first. And to do the derivatives over time, to take a time derivative, we just take this out. So it will be times minus lambda and times the same exponential. So that's the answer for the induced voltage, electromagnetic force. Seems to be correct. Yes. So what about the direction of the induced current? The direction of the induced current can be found by Lenz's law. And Lenz's law says that the direction depends on the change of magnitude of the flux, which passes through the area, in this case, curve C.